All right. So we are going to give a short video introducing today's topic. So this week we are going to talk about matching. Okay. So matching is just a disjoint union of edges. Okay, so this is a matching. So uh, it's a very simple object. So we also define something called perfect matching. So a perfect matching of a graph G is a matching. So first it's a matching which covers the whole vertex set. So what's happening is that so you have a graph G here, and then we choose. So first, G must has two m vertices. So the number of vertices of G must be an even number, and then this matching is called a perfect matching if it contains all the vertices of G. Okay. So we say that m the size of the matching is m. Okay, so each edge covers two vertices, so there are m edges, so it covers all the vertices. So this is the situation we call it a more perfect matching. So there is a very famous theorem. So I will try to prove this theorem in this first recording. So it's called House marriage theorem. So it gives a criterion for bipartite graph to contain a perfect matching. Okay, so we work with a bipartite graph. So on the vertex bipartition, that V of G equals AA union with B. So there is a bipartition, two parts. And the Hall's condition is the following. So the let's say G on AB. So let's say for convenience, let's say A and B each has a size n. So each has a n number of n vertices. So this bipartite graph admits a perfect matching, which we say PM, if and only if. So look at A. For any subset, say X of A. So if we write the neighbor set of X as all the, so for example here I got a set X. So here the larger one is set A. So we will look at the neighbor set which we call n of X. So it's just the union of all the neighbors of every vertex of X. So maybe we should define n of X to be the union of all the y in B. So here is the big set B here, such that x, y is in the graph G, is an edge of the graph G for some x in X. Okay, so this is a standard definition. We call neighbor of X, meaning the union of the neighbors of each vertex of X. So okay, so maybe we should put all X in x, and we write n of x, neighbors of x, the union of area. So, okay, so this is the definition. So let's come back. So this sentence is that for any subset x of A, n of x, the size is small, is at least the size of x. Okay, so for every subset x, its neighbor is larger, at least the same with the size of x. Okay, so this is the criterion. So this property usually is called Hall's criterion. So if you have this criterion, it ensures you that bipartite graph meets a perfect matching. So this is kind of famous. Many people in different areas of mathematics, very surprisingly, they found that, okay, this criterion can be applied to prove something, even in geometry, in other areas. So it's a very commonly used criterion. Okay, one direction. Let's try one direction which is easier. So let's prove the if you have a perfect matching. So suppose, I think this direction is easier. So but I use this to review, to understand this Hall's criterion. Suppose there is a perfect matching. There is M, which covers a perfect matching. So let's say there exists a PM, which is called M. Okay, so it's a perfect matching. So if we take x0, for example, of size k. So x0 is a subset of A. Okay. So, right? So I think it's very simple, because this is x0, and the perfect matching means that this is a perfect matching, right? Every vertex is matched by this M I have. So following this matching, these vertices, clearly all of them belong to a neighbor of nx0, and these vertices already has the size of nx0. So it implies that n of x0 size is greater or equal than the size of x0. So checked. That is very simple. But the other direction we need to prove using induction. So we induct by the size of parts of the graph. So of A equals B. Okay, we need clearly we need A and B to have the same size. Otherwise, there is no way to find the perfect matching. Okay, so we induct by this. So remember we are trying to show that with the criterion of Hall, this matching, this graph, bipartite graph, admits a perfect matching. Suppose this is true for all smaller. So say this is n. Okay. So case 1, base case. Suppose n is 1. I think it's very clear, right? So you have A and B maybe. So there is an edge. Okay. Because you must have this edge. If you have an empty graph, then the neighbor of A is 0 and A is 1, so it's smaller. It doesn't satisfy the Hall's criterion. Okay, so this is easily checked. So for n equals 1, if you have Hall's criterion, you must see this picture. And maybe we put case 2, and there are 2 subcases. In fact, so no, maybe this is the base case. Let's say base case. Usually, okay. And now, suppose by induction, suppose that the conclusion is true. So the statement Hall's criterion implies perfect matching. This is true for any smaller graph. Say any bipartite graph with any smaller graph, smaller than n. Okay, so suppose we have a equals b equals n, and this is sort of the first, the minimum counterexample for any bipartite graph with a size smaller or equal than n minus 1. The conclusion is correct, and okay, and then we have so two cases. Case 1, for any k set x in A, the neighborhood of x is actually greater or equal than k plus 1. So it's okay, you see the criterion of Hall says that this is at least k. So k set means that the size of x is k. But we are looking at a further case, saying that for any k set, actually this is stronger. So it's greater or equal than k plus 1. This is easy to deal with, but let's do this first. So if suppose for any k set, k smaller or equal than n minus 1, okay, at least one less than n, okay. So suppose this is true, then this is the thing that we choose only one edge. Let's say xy in G, okay. So then we look at G prime equals G minus xy. Okay, so for example, we put any xy edge, and you consider the remaining G prime. So G prime is a bipartite graph with each side has n minus 1 vertices, and then we want to use induction hypothesis. So by induction hypothesis, so any, for example, x prime here, so let's check. So for any x prime in, for example, a minus x prime here, so what is the nx prime size? So it is clearly greater or equal than x prime size, right? Because there is a possibility that y belongs to it, but we have a stronger assumption in the graph G. So if you forget about vertex y, you still have this. So Hall's criterion is checked, is verified for the graph G prime. So then, but G prime has less vertices. So by hypothesis, by induction hypothesis, we have that G prime admits a perfect matching. So that's fine, because what we have shown that we take out one edge and the remaining graph has a perfect matching. So together, G has a perfect matching. This concludes with the induction step in case 1. So in case 2, so in case 1 said for any k set you have this. In case 2 that you can assume for some k, smaller or equal than k minus 1, we have x. So there exists x which is subset of A. X has size k, and the neighborhood of x is exactly has the same size. Okay, so the picture will be like this. So we have x here, and here we have the neighborhood of x, and you have edges here, and there's no edge from x to here. So we define this set to be y and this set to be y prime. Okay, so in other words, y is a minus x, and y prime will be b minus n of x. Okay, so what happens here is that for any, for example, let's say z, any subset z of y. Okay, so the neighborhood, let me see. Yeah, right. The neighborhoods, yeah, I think it's better to put a subset here. For any subset z prime here, the neighborhood of z prime, so because this set does not connect x, so all its neighborhood is in y. By the original house criterion, this is greater or equal than z prime, and this belongs to y. So this means that in the bipartite graph G, y prime house criterion holds 2. So by induction hypothesis, we know that there exists a perfect matching here. All right? And also there is and inside, so similarly, there exists a perfect matching. So here is a perfect matching in G, y prime. And here there exists a perfect matching in G, x, n of x. Right? So together, we got a perfect matching in G. Okay? So it's induction. Okay, this is a classic. I don't think it's very hard. So let me stop here. And in the second part, when we meet, I will introduce some other techniques about matchings and perfect matchings and something called maximum matching. So in the case that you don't have a perfect matching, you will look for some matching which covers as many vertices as possible. Okay, see you later. Okay, so let's prove a theorem. Let's first recall that a bipartite graph BG is bipartite by two parts, A and B. And so theorem. So the matching number of G equals the covering number. Okay, so we can define this as a covering number, which is the mean size of a set which covers all edges. Okay, so this is an informal definition. So we are trying to prove this identity. So let's first we see this direction. Okay, so if we have any matching, right? I think it's clear that if I take any matching M here and a covering set, let's say S has size at least, for example, it has size R. So this has size at least R. I think it's pretty clear. Any set, vertex set, with size strictly smaller than R, you cannot cover this matching. You see? To cover this matching, each edge use different vertices. So to cover this matching, you already need at least R vertices. So this proves that because this is true for all matching, so you take a maximum matching which realize your matching number, then you prove this direction, and the difficult one is this direction. Okay, so we are trying to prove a matching number. Let's say matching number is at least covering number. Right? Let's try to write down exactly what we are trying to prove. Given M, which is a maximum matching, we will find a set. Let's write D now, okay? So because in our proof we will find a set D with the same size with this matching, and the D covers E of G. So every edge in E of G will have at least one end vertex belonging to D. Okay, this is the goal. So let's draw many pictures. So this is the maximum matching M. Okay, we will define U to be the unmatched vertices in M. Okay, so this is the set U, which is the set of all the unmatched vertices. And at this point, we will consider all the M alternating paths starting from some vertex of U and ending at B. I don't really care where it ends. Okay, so this is a set B. So I need this path to start here. For example, this is my x0. So since it starts from U, it means the first edge is not an edge in M. Okay, so this M alternating path, the first edge is not in M, and the second edge has to belong to M. So not in M, not in M in M. Oh, so this is the M alternating path. So at this point, I want to pick every edge from this matching, and I choose exactly one of its end vertices to put it into my set D. Okay, so I define this rule. So for any edge AB in M in my matching, if there is some m alternating paths. So this path we considered starting, let's repeating again, starting from U, ending at B. Okay, so for one edge AB, we look at this end vertex B, this one. So this is A. This one, this is B. I look at this B. I ask if there exists any M alternating path starting from U and it ends at the point B. If this is true, we find some M alternating path starting from U ending at B, then we put B in the set D. Otherwise, so meaning that there is no single M alternating path starting from U and ending at B. Otherwise, we put A in D. Okay, so in each for each edge in our matching, either B is in D or A is in D. So naturally, you have the size of D is exactly size of M. And then we want to prove that D is actually a covering set. It covers all the edges. Okay, this is very interesting, because the proof is that if it does not, you can somehow find augmenting path, which will increase your matching and contradicting that this matching is maximum. Okay, so we have a final claim to prove. Claim is that D covers G, E of G, all the edges, E of G. Okay, so let's draw a picture here. For example, this is my M. This is my M, okay, and this is my set U, unmatched set in A. So the first case, we let's see. So if an alternating path, M alternating path starting from U arrives at B, for example, some vertex B. Okay, then so this path, so let's call it P. Then P, the path P cannot be an augmenting path, because otherwise you can find a larger matching, right? Okay, so it implies what? So because you somehow for example, you arrive at B. This is alternating path. You arrive at B, and but P is not augmenting path, right? So I mean, okay. So let's see. We don't have information about B, so we make it a little. So we have this. We know this is an edge, because we start from some vertex in. Okay. So we start from some vertex X here, and we start with an edge which does not belong to the matching, and then the next edge has to belong to the matching, and then, for example, I arrive at B. Okay, but this cannot be a augmenting path. So B, meaning that B must be covered by M. Okay, so remember the definition of augmenting path. You have this not in x0, not in this edge, not in M, and edge in M, edge not in M, and edge in M, and you have to finish. At a vertex which is not in M. This edge is not in M, and also the starting vertex and the ending vertex are not covered by M. Okay, so we arrive at this point B as our end point, and this path P is not augmenting path, meaning that B must be covered by M. If it's not covered by M, we got augmenting path, because X is not covered by M. We start from this X which is in U. Okay, so B must be covered by M. But by our definition here, if there is a M alternating path starting from U and ending at B, then we already put B in D. So it means that B is in D. Or we can say that D covers the vertex, D covers the edge AB, because B belongs to D. Okay, so this is an observation. Now we take AB, any edge, an arbitrary edge. We want to prove either A or B belongs to D, and we are finished. Okay. So case 1, A is in D, then we are done. So case 2, A is not in D. Okay, and A is not matched. Okay, A is unmatched. Okay, so it means that A is from U here. This is U, and B, as we said, this edge is not matched, and B must be matched. B must be covered by M, because otherwise, if B is, in this case, if B is also unmatched, then we can add this AB edge into the matching, such that we obtain a larger matching. This is actually part of this argument of case 1. Okay, because one edge exactly is a alternating path starting from a vertex from U. So it's not possible. Okay, so we conclude that B is matched. Okay, A is unmatched, then B is matched. And since B is matched by our way of defining D, B belongs to D. So D covers the edge AB. Okay. The third case is that A is not in D and A is actually matched. A is matched. Okay. So if I draw the picture, so we don't quite care about unmatched A because we already deal with it. So suppose A is matched and AB, but we don't know AB is in the matching. We don't know that. For example, we draw AB like this. Okay. So since A is matched, So we assume that AB prime is one of the edges in our matching. So this is B prime, AB prime. Okay, we have this picture. So we know that this guy is in M, and this is not in M. Okay? Right. So if B is in so let's see. Okay, so let's see, because by definition of the okay, so B prime, there exists an alternating path P to B prime. Why is that? B prime is in our set. Yeah, right. Because we assume A is not in D, right? And in the AB prime is in the matching. Okay. By our definition, we must have already chosen B prime in the set D, and the reason to do so is that there exists alternating path P from U to B prime. To B prime. Okay, so there is some X. We have this alternating path, and we arrive at B prime, and we know this. So this is the picture. And we don't know case 1, let's say 2.3.1. So the vertex B, so this is the path. This is the path from X to B prime. The first sub case is that B, the vertex B, I draw here, actually belong to this P. So it's like this. Okay. Then by this picture, we see that from X to B, along this path P is a subpath. So from X to B, this, if we write this as P prime, then P prime is also an alternating path. Okay, by definition, it means that B must belong to D. Okay, we are done. Because we are interested in this edge AB. We hope B belongs to D, because we assume that A is not in D. So this edge AB, A is not in D, we have to prove that B is in D, such that D covers this edge. Alright? So the second case is that B is not in P. So the picture should be, let me start from X and arrive here, and I got here, this is, I don't know what it is. So I got here, and this is B prime, and this is A, and this is B. Okay, B is not in this path. But now I consider P starting from X to P prime, right? I put the endpoint P prime here, and I continue. AB prime, you see AB prime is an edge in M, and look at this. AB prime is an edge in M. AB is not an edge in M, right? So I continue with this path. I write P, B prime, A, B, this guy. It is a augmenting path, alternating path. I don't know, it's augmenting. So alternating path. So it's an alternating path and ending at B. By definition, B must belong to D, but the choice of D. So it means that D covers AB also. So in all cases, D covers all edges. Okay, so this is the full proof. It's a little involved. So the key is to use idea of augmenting paths and alternating paths. So let's finish the recording. I shared my screen, so can you hear me? Everything is fine, right? Great. We continue to talk about matchings. Matchings they are not a very difficult object, but they are very hot topic. It's a very hot topic in recent researches. So there is one thing I think it's a little surprising, is that let me say, to find Hamilton cycle in a graph. So clearly, if you have a Hamilton cycle like this, you, for example, it's the graph has a even number of vertices. So if you, my cycle is not very good. So let's say like this. Okay. So you have this is a Hamilton cycle. It covers all the vertices. So you look at the edges, every other edge. So you take an edge here, 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 and okay, final edge will be this edge. So it's a matching. You see. So in fact, let me write in red. Hamilton cycle clearly contains a matching, a perfect matching. If say G has even number of vertices, contains. Right? Is it clear? So I'm saying that if you have, for example, a cycle like this, so then you just you take this edge, this edge, this edge, and this edge, right? And it's a matching. So somehow in many problems, people ask if some graphs has a Hamilton cycle. They first try to look for a perfect matching. So it's a simpler task. So because Hamilton cycle always contains a perfect matching. If you don't have a perfect matching, there's no way to contain a Hamilton cycle. And on the other hand, if you are somehow find a perfect matching, then you try to connect. So for example, this is a perfect matching in your graph, and then you try to connect, right? And then you have a Hamilton cycle. So this it's a way. So at this point you haven't seen much, so you feel it's still complicated. But it's in the higher level, it's an idea how to prove many theorems. So let me come back to the topic of matchings. So in a graph, if you don't have a perfect matching, so let me continue. We will call in a graph G probably you don't have a perfect matching. So you will call a maximum matching. Okay, so for example, I'm if uh, M which covers maximum number of vertices. Okay. So sometimes we are the size. If you have a maximum matcher, maximum matching, then its size is called matching number of M. Okay. So it's natural, all natural. Okay. So we have some other definition. This is a kind of a natural. So let me so define some other objects. So suppose we have a matching. Suppose M is a matching in G. So if you look at the graph, will be something like this, and this is my whole graph G, and usually we just write this as a matching. So it's okay. We don't know other information. We don't know if it's a maximum or not. So we define a path in the graph. So let's say an M alternating path of G is such that so it's a path. So alternatively, the edges belong or not belong to G. So what to EG, the edge set of G. So what I'm saying is that you have an edge here, so it's a path, but this edge is the edge of my matching, and this edge is not, and this is so okay. So it is still the edge of my graph, but this edge belongs to my matching, but this edge does not belong to my matching. And for example, this F belong to my matching, and the next one, maybe I don't know. I mean, I use blue to say something not. I don't know. It's really confusing. So really, so this path itself is a path of my graph. So every edge, let's write this guy E in my matching as black, and then I write this red. For example, F is not in M. Okay, so this is a definition of M alternating path of G. Is it clear? So it's a path. Don't get confused. So it's a path. Every edge E F, for example, F2 is not in M. Maybe here E2 is in M. Okay, but all of them are edges of G. It's a path, but somehow one belongs to M, my matching, and the other one does not belong to M. So this is the definition of M alternating path. All right, is it clear? Great, great. So we also talk about alternating cycle, which is not which is not very different. So you have this E, and maybe you have some E2. Okay, E1 is an edge of M, E2 is not, and maybe E3 is the edge of M, and E4 is not. Okay, so, so sometimes we just use this kind of dashed, but we have colors, so we can use different color. But anyway, this is a path, and this is an alternating cycle. I'm alternating cycle here, this guy. Okay, so so there is another further definition. Okay, something called I'm augmenting path. So this definition, you try to understand it, and you will know, you will see why we define this thing. So it's a path such that first is a alternating path. Okay, and starting from V0 for V1, starting from V1, V2, and until VK, for example. So this path, I will not, I haven't draw the edges because I want to say that such that with further condition that the first vertex and the final vertex VK are not covered by the matching M. It's a very strong condition here. So for sure, it must start with a non-edge. Sorry, non-edge from the matching. I mean, start from edge which is not from my matching, and the second edge is in my matching. This is M, and the third is not in the matching, and finally, the final edge is not in the matching. And this, for example, this VK minus 1, this edge is in my matching. Okay, so it must be this, and not only this. There's no matching covering V1. There's no matching covering VK. Okay, so this vertex V1 is not covered by my matching. So this path is called I'm augmenting path. So this path is in the hope of change my matching to grow the size of my matching. So you will see, because once you see, since once so given such an M augmenting matching sorry path for the matching M, what we can do? What can we do? We can change this kind of thing we have seen before. It's really similar to what we have seen several times in graph colorings. We want to sort of change the color. Okay, so in this case, you see, it must start with red. For example, let's for simplicity, you have 3 edges. Okay, so it must be like this. If we found this, we decide to change the definition of the matching such that the matching will be like this. Okay, so this is a new matching. So we want, if we have this, we flip the colors. So the color is defined as okay, red does not belong to my matching, and the black belongs to my matching. So we flip the colors such that a new matching. So we only change the definition partly of the matching, but a new matching is defined. Say M star. and clearly M star is a larger matching. So in particular, this M was not maximum matching. Is the process clear? How the definition is given? Here we obtain a new matching. Let me give a really concrete example. So I have a Peterson graph here. So let me draw this. So this is a Peterson graph. So how? So let's call this V1, V2, and you have edges here also. And V3, V4, V5, V6. This guy is V6. So I give names for 6 vertices. And I define a matching. This is my graph G. I draw all the edges. Now my matching is this. So I put a V1, V2 here. And I put a V3, V4 here. And I put a V5, V6 here. So this is matching. This is my matching. I only look at this matching seen as a subset of edges, right? Must be disjoint. So the size of my matching is 3, only this. And somehow, okay, I defined many things. I want to find a path which is here. There is a vertex. This vertex. I draw them. This is not belong to my matching, so I draw red. And this oh, right. Sorry, I think I got another I got another edge. I can. Okay, my matching has 4 vertices. First, 4 edges. My matching has 4 edges. This is my matching M. I don't have a name for this, but I put this edge also. Okay. So my matching has 1, 2, 3, 4 edges. This is my matching. And then I found this path. So the path starts from this edge, which is not from in my matching, and I got this edge, and this edge, right? So by definition, this path P here is M augmenting path. So I can flip. By flip, I just put this edge, and this edge, this edge, and this edge, and the rest is red, right? I change the color, and I don't touch the first edge, so I get a new matching which has 5 edges. Okay, so this is the idea. So here comes the theorem, which we call Burgess theorem. Burgess theorem. This says a matching M in a graph G in G is a maximum matching if and only if G contains no M augmenting path. Okay.
Okay.
Yeah. Actually, what we have proved is this. What I explained here is one direction of this theorem. So if you have, so which direction we have to think? So if we have M augmenting path, then M is not a maximum matching. Actually, it's this direction. Because we actually prove that if G has M augmenting paths, then M is not a maximum matching. So we kind of reversed the statement. So it's in this direction. This is that. We just use this color flipping idea. Okay. So the other direction we have to work a little bit. So what we want to do is still again we want to make the converse the equivalent statement. Suppose M is not maximum matching, and then we want to look for M augmenting path. So it is enough. It's really we say it suffices to prove that there exists an M augmenting path. Okay, so we do that. So what happens is M is not maximum means that there exists M star another matching which contains more edges. This is strict. All right. So what here is a little abstract, but I think it's very beautiful. So what happens is that we're trying to look at a graph which is strange. It's the symmetric difference of M with M star. So what is the symmetric difference? A symmetric difference as a set theory. So if you have a set A and set B, the symmetric difference of A and B, it is A minus B union with B minus A. So in fact, is this part union with this part. Okay, so it is so the part A union B, but you have to minus the part of intersection. So it's like this part, this special part. Let's draw red. This special part red has been covered twice, and somehow you don't like it. You delete it. You only remember all this part that's been covered once. So if you define a graph as a symmetric difference of two graphs, it means that if an edge, so let me make a more clear. So this graph H, how do you define it? So an edge E belongs to H, if and only if E belongs to M. So it's just let me how to say. So an edge, let me say. So an edge E in G, if E belongs to M and belongs to M star, then it is not an edge of H. But if E is in M minus M star, or E is in M star minus M, then E is in H. Okay, so the edges, the edge which belongs to both matchings, we don't put it into H. So this is the definition of a symmetric difference. Okay, so in this case, for example, if V is for example, is covered, any vertex is covered by M and also covered by M star, there are two cases. If V is covered by the same edge, by E in M and in M star, so this edge belongs to all of them, then in H, V is not covered. So this definition really it solves a lot of things for our arguments. Okay, so if we, for example, again for this big situation that it is covered by M and also covered by M star, but if V is covered by E in M and E prime in M star, E star in M star, say, two different edges. Then okay, it's then in H, with E is covered for sure, and its degree is 2. I mean, this is E in my first matching, and this is E star in my second matching, and this is V. So this is a part of H. In H, the degree of V is 2. So two edges are both present because the definition. So unless they are the same edge, then they disappear. So in this case, degree of V is 0. So in this case, degree of V is 2. Okay. So if V is not covered by anyone, it's not covered by anyone. And also, if V is covered by M but not by M star, then the degree of V is 1. So you have this E. Okay? So it's a little abstract, but you think about this definition, you got this. So you just consider the symmetric difference of all the edges of M and M star, and you get this. Okay? So look at all the situations, you see that the degree of V is 2 or 1. Imagine in the graph H, all vertex, the degree of V is smaller or equal than 2. So what is this graph? So this graph H, it must be a union of paths and cycles. Okay, maybe not connected, but you see some. So in case 1, let's look at one connected component that a cycle. Let's say a cycle C is a connected component of H. Okay, so every vertex has degree 2. The only situation that you see degree 2 is this situation. You have two edges. One belong to M and the other belong to M star. So you conclude with a alternating path, sort of. So this edge E1 belong to M, and another edge E2 belong to M star. You have to see this. So it's a cycle. Here is E3 belong to M, and you have E4 maybe belong to M star. This is the only situation. Okay, so this is a cycle. So if all the connected components are cycles, we will get that M and M star have the same size, which is not true because we have taken M star to be a larger matching. So we conclude that there must be a case 1. So well, maybe not a case 1, case 2. So let's say if a cycle is connected component, then by this argument, since M star is a larger matching, okay, so there must exist a connected component which is a path, not a cycle. So there are only two kinds of connected components, path or cycle. So there must exist a path. Not possible that all components are cycles. So if there is a path, and this path is special, so the starting edge must belong to M star because M star is larger. And the second edge belongs to M. And then, so here is a edge from M and the final edge from M star. So there is one more edge. The number of edges in M star is one more than number of edges in M. So you have this situation. But this, if you look at this, this is exactly M alternating augmenting path. Okay, so this is what we are trying to show. So so let's recall this proof. So Birch's theorem saying that a matching M is a maximum matching if and only if G contains no M augmenting path. For this direction, suppose M is not maximum matching. We try to construct an M augmenting path. And for that, we have to borrow some other matching which is larger and use this kind of constructed graph, which is the symmetric difference of A and B, and we conclude. Okay? So there is another theorem. I don't know if maybe we can continue. I don't know if you are energetic or not. Okay, let me see the question. M star has number of edges. Yeah, no. It's enough to assume that M star has a number of edges strictly more than M. Okay, so why is that? So because I'm talking about connected component. So it's possible if M star has a way much more edges, it's possible some connected component is just like this. This is a component. Both V and W are not covered by M. It's a special case of this argument. So the path length has one, and then I change it to it. You can call this. You can call this M augmenting path because both V and W are not covered by M. Is it okay? But then there will be more edge inside the cluster. No. 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 How to explain this? So, because here is a full argument. So H, why we take this effort to define this H? So we actually prove that in H, which is obtained by this symmetric difference, and we prove that every vertex V has degree 1 or 2 or 0. Then we conclude that in H, it must be union of paths and cycles. And we prove that they cannot be all cycles and at least one path. This is a path. This is path. For any path taken, it must be a M augmenting path. There is no other situation. There is no more edges in between. Is it okay? Okay, it's nice. I mean, it's a very nice question. Yeah. So to make sure I can explain some confusing parts. But it's a decent proof. It's nice proof. Okay, great. I mean, we take arguments to arrive here. If you look at the conclusion, you might be confused. But actually, we prove something step by step. So in H, every vertex has degree at most 2, and then there is only possibility the connected components are cycles and passes. So okay, so let me finish with another. I don't know if I can finish the proof because it's a little complicated. So so maybe I'm thinking maybe I send another video for you guys to explain one more proof. But before that, I'm going to give the statement at least for this stereo. So so we give another definition. We call a vertex set. So let me have work with a graph G. We call a vertex set A okay, we say it covers, say a vertex subgroup A subset A covers G if all edges has relations to it. All edges of G has at least one end in A. Is it okay? So it's like you find a vertex subset. All edges, there is no edges here. No edge here. No edge here. Okay. All edges must have some relation here. So it must, and maybe both ends are here. It's fine. So we say A covers G if all edges of G has at least one endpoint and vertex in A. Okay. So there is a theorem I want to explain, but the proof is a little involved. I want to maybe send a video to you guys. So let me work with G bipartite graph. On 2 parts, A and B. So you have this A, this B. G is a bipartite graph. Okay. So in this case, the matching number, let's say maximum matching size. So this is the definition of matching number of G equals the minimum covering number. So covering set. So let me minimum size of covering set. Okay, so what happens? What is the theorem? So let me try to find the maximum. So for example, this is M. So this is a bipartite graph. So the matching has to be something like this. So this is the maximum matching. For example, it has a size R. Okay. So what is the covering set? So we choose some vertex here and some vertex here. So all the edges, either something here or something here, and then maybe something between. So for example, in this case, my covering set S has size 6. I just choose some vertices, and I ensure that all the edges must has one end vertex in my S. And my goal is choose as minimal as possible. So as it turns out, these are two numbers are the same. But the proof uses augmenting path. Okay, it's a very interesting proof, but it's a little harder than the proof I just give. So I think I don't want to confuse you. I'll send you I think 20 minutes second video later today before today. Okay, I think it will be easier. Otherwise, it will take me another half an hour maybe. Okay, let me stop the recording.